I'm going to talk a little bit more about integration today. I really need to explore that corollary to the Fundamental Theorem of Calculus, which we proved last time. The Fundamental Theorem of Calculus itself is a really important theoretical tool, and we'll use it later on in the course. But the corollary is that striking computational tool which gets used absolutely all the time. So let's just quickly remind you what the corollary was. The corollary connects the definite integral to the indefinite integral. So the definite integral, that was the area, the integral from a to b f of x dx. So for this corollary you need that f of x is a continuous function. And so this definite integral is the area under the graph between x equals a and x equals b. Whereas the indefinite integral, that's the thing I simply denote integral f of x dx. So this meant, remember, this meant any explicitly given antiderivative of the function f of x. You really need to know what that antiderivative is for this corollary to be useful. So it's some function of x which, when you differentiate, gives you f of x. And you remember many people religiously, when they write indefinite integral, they write the function plus c, but I never bother doing that. It always seems a bit pointless, so I just pick my favorite antiderivative, and I just remember that it's only well defined, it's only unique up to adding a constant. So you take that given function, that given indefinite integral of f of x, and then you evaluate that function between x equals a and x equals b, and the corollary says that that evaluation of that indefinite integral calculates the definite integral. So this is remarkable because it says as soon as you're lucky enough to know an antiderivative for f of x, you can explicitly calculate the area under that graph. So this was the revolutionary breakthrough which Newton and Leibniz realized at the end of the 17th century, roughly 1660s, 1670s, and that was the birth of calculus in my mind. But I think you need to understand that the time was ripe, 1666. The time was just ripe for this discovery to be made. There were lots of things in place at that time without which that discovery could never have been made. Although Newton and Leibniz were two absolutely brilliant people, they were also sitting on top of a body of mathematics that had been developing for hundreds, if not thousands of years. In fact, the idea of computing areas by cutting up into strips, that was a classical idea. The greatest user of that idea was probably Archimedes, and hopefully you're doing the readings that I'm recommending on my webpage along with this. And in the readings last week, you would have read a little bit about Archimedes, and you would have seen his totally ingenious and brilliant proof for calculating volume of sphere. He could calculate the curved surface area of a sphere, areas of circumferences of circles, all of that sort of stuff. He totally understood how to do it by this basic method of cutting it up into little tiny pieces and then summing. So certainly this was all resting on that classical mathematics. I think there's one other theorem that's worth pointing to, and I want to talk about that right now. So that was a theorem of Fermat. From roughly, it was in the 1650s, I forget the exact date, and that clearly pointed to a connection between derivatives, or well, really antiderivatives, which is just differentiation done in the inverse direction, and the problem of calculating areas under graphs. So here's what Fermat's theorem could do. Fermat could calculate the area under the graph y equals x to the n for a natural number n. So in the notation we're using, he could calculate the integral from a to b x to the n dx. So let's just draw a little picture so that you're on board with this. So this is the graph of y equals x to the n. So it's, if we go to n is 2, it's a parabola, but it needn't be a parabola. It can be steeper, it can be a cubic or a quartic. And we're looking at that graph between a and b, and we're interested in calculating that area of that region underneath that y equals x to the n curve. So let me see, what are we expecting this to be? Well, we're much luckier than Fermat. We know the fundamental theorem of calculus. So we know this is extremely easy. All we have to do is find an antiderivative for x to the n, which we can do using the inverse power rule. Add 1 to the power, divide by the new power, and then we have to just evaluate that from a to b. And so it's b to the n plus 1 over n plus 1 minus a to the n plus 1 over n plus 1. Right, so that's exactly what Fermat proved. In fact, Fermat, what I'm going to show you is Fermat's proof just in the special case that the bottom edge of the strip, this a, is actually 0. So I'm just going to show you how to calculate the integral from 0 to b x to the n dx. So that's just this b to the n plus 1 over n plus 1. And then by subtracting two such regions, you can obviously calculate that more general formula that I've just written down. But you see, when you see this quantity b to the n plus 1 over n plus 1, and you know the power rule and you know the inverse power rule, it should sort of jump out at you that, oh, this is weird. This area, that seems to be the antiderivative calculation for the power function. And I'm quite sure that Newton was well aware of that, and when he was thinking about derivatives and antiderivatives, he would have known this inverse power rule. And Fermat's formula would have just jumped out at him and said, look, there's got to be a connection. These areas under graphs have got to be to do with antiderivatives. So I want to just, not only so that you are aware that there was this history in place, this theorem 20 years earlier of Fermat, which would have been very suggestive to Newton, but I want to show you Fermat's argument, because he didn't have derivatives or any of this theory in place. He just computed this area under this graph by cutting it up into strips and summing. But it's such a brilliant argument, I want to show it to you, so I'm going to quickly explain. So here's Fermat's proof. So I need a little bit of background. I need a prerequisite to explain this. And the prerequisite has to do with geometric progressions, or geometric series. So what I want to do is show you how to calculate the sum of this geometric progression, 1 plus t squared plus t cubed and so on, all the way up to t to the n. Okay, so that's called a geometric progression. To get the next term from 1 to t, you have to multiply by t, and then to get from t to t squared, you multiply by t, multiply by t. So each term, the ratio of the next term to the previous term, all the way along this sequence is t, and then we've got to add up these terms. So let's see if we can calculate that. So I'm going to just calculate that quickly. Let's call it S for short. And then the observation that lets you calculate this rather easily is if you times S by 1 minus t, so if you FOIL that out, that's S minus TS. And S is, what is that, 1 plus t squared plus t to the n minus 1 plus t to the n. and then I've got to subtract ts. Well, t times s is t squared, t cubed, t to the n minus, t to the n minus 1 times t is t to the n, and then what is the last one is t to the n plus 1, right? That's coming from that t to the n times t. Okay, so that's that quantity, and that looks a bit horrible, but if you look at this, you see that there's a t and a minus t, there's a t squared and a minus t squared, there's a t to the n minus 1, and right there's a minus, and then there's a t to the n minus, so all you're left with, everything cancels, except for the very first guy and the very last guy. And now if you divide both sides of this equation through by 1 minus t, so t had better not be 1, then you get that s is the right-hand side 1 minus t to the n plus 1 over 1 minus t. Okay, so that's that calculation, how to sum the geometric progression. So we found that it's equal to 1 minus t to the n plus 1 over 1 minus t. Let's box that in, because that's a pretty basic and fundamental fact that everybody should know. Didn't work. Let's try that again. To fill it in, there we go. Okay, so that's the first very important little fact that you should know. Hence, providing the absolute value of the number t is less than 1, the infinite sum 1 plus t squared plus t cubed forever, so just don't stop, keep summing, that infinite sum is equal to 1 over 1 minus t. So this is called the geometric series, and this is the very important formula, maybe the most important of all infinite series, the formula for the sum of that geometric series. Why? Well, what we've got to calculate is the limit as n goes to infinity, 1 plus t squared plus t to the n, right? We're trying to do the infinite sum forever. Well, that's doing the finite sum, stopping at t to the n, but then letting n go to infinity. That's what infinite sum means, which is the limit as n goes to infinity. Now we've got the formula for that, is 1 minus t to the n plus 1 over 1 minus t. And now we need the fact that the absolute value of t is less than 1, so that as n goes to infinity, that's a number less than 1 being raised to a bigger and bigger power. So that term there tends to 0 as n goes to infinity, and that leaves us with 1 over 1 minus t. Okay, so that's what we need to give Fermat's proof. Now let's go ahead and show you Fermat's argument. So we're looking at some sort of y equals x to the n graph. There we go. And we want to be at B, right? We're trying to calculate the area under that graph. So here's how it goes. So Fermat's genius idea was not to cut that area that we're trying to calculate up into strips of equal width, delta x, like we were doing last time when I was explaining quickly the idea of integration. Fermat's idea was to cut it up into unequal strips. So he wanted to take some 0 less than t less than 1 and consider strips at x equals b, x equals bt, bt squared, bt cubed, and so on. So the next strip will be at bt, and then we'll go to bt squared, and then bt cubed, and bt to the 4, and so on, and t is less than 1. So there's going to be infinitely many little strips, more and more and more, the closer you get, thinner and thinner and thinner strips. But we're cutting that region up into these strips. Okay, and then what we're going to do is we're going to look at these little upper rectangles up above the graph of these widths. And we're going to sum up the area of these upper rectangles. Of course, they overestimate the area that we're trying to calculate, but as the strips get thinner and thinner, the error will get smaller and smaller, and it'll become exactly what we're trying to calculate. So we're going to sum the upper strips as shown, and then we're going to let t approach 1 from the minus side, so that we're going to make this first strip get thinner and thinner and thinner, and so on. All the strips get much, much thinner, and so the error up above will get smaller and smaller and smaller. So in that limit, as t approaches 1, the formula we're going to calculate will approach the exact area that we're after. Okay, so the area of the upper strips is what? So okay, let's start with the rightmost strip. So let me see, what's the height of that rightmost strip? That's x coordinate is b, it's y equals t to the n. Sorry, y equals x to the n. So the height of that strip is b to the n. That next height will be bt to the n. So b to the n, t to the n, and then it'll be b to the n, t to the 2n, and so on. You can't really read that, but let's so what's the rightmost strip? Its height is b to the n, and its width is the difference in the x coordinates, b and bt. And then the next strip along the second from the right, its height is b to the n, t to the n, and its width is bt minus bt squared. Then the next strip is height b to the n, t to the 2n, and its width is bt squared minus bt cubed, and so on. It's an infinite sum because there's going to be infinitely many of these strips. So what is that? Let me see. Everything's got a b to the n. Each of these brackets has got a b in it, which I'm going to pull out the front. So actually I've got a b to the n plus 1 out the front. And then that leaves me what? That leaves me 1 minus t from the first term. It leaves me, looks like t to the n, t minus t squared, and t to the 2n, t squared minus t cubed, and so on. And actually, each of these terms, there's a 1 minus t. This is t times 1 minus t. This is t squared times 1 minus t, and so on. So I can, hang on, that looks wrong. Let me just fix that up. That was meant to be a b to the n plus 1 there. So I can pull out a 1 minus t from everything. And then that leaves me with what? 1 plus, there's a t to the n and another t. There's a t to the 2n and a t squared, and so on. So we actually got t to the n plus 1, and here there's t to the 2n plus 2. And then the next one will be t to the 3n plus 3, and so on. And now we can sum that, because look, I've got a geometric series. It's b to the n plus 1, 1 minus t. So this sum, okay, it's a geometric series where the ratio isn't t, the ratio is t to the n plus 1. So the sum is 1 over 1 minus t to the n plus 1. And I'm not quite done, because if you look at this, what I've got here, this is just like our formula for the sum of the first n plus 1 terms of that geometric progression, except it's the reciprocal of that formula. So that's actually just the reciprocal of that sum. So that's what I'm going to write in here. So I've got this b to the n plus 1, and then that 1 minus t over 1 minus t, that becomes the reciprocal of the geometric progression up to t to the n. And now I'm going to take the limit to calculate the final area that I'm after. That's going to be the limit as t approaches 1 from the negative side of that quantity. But this is a very easy limit to calculate. T is approaching 1, so in this denominator I've got n plus 1 terms, each of which gets very close to 1. So in the limit, that denominator becomes n plus 1. And that's exactly the inverse power rule formula that we were trying to calculate. That's Fermat's theorem. Okay, great. So what I want to do for the rest of this lecture is do a few more examples of calculating areas, volumes. I'm not quite get there today, but next time I'll start talking about arc lengths as well. Calculating with this amazing tool, this corollary of the Fundamental Theorem of Calculus. I'm doing this partly so you appreciate what a cool tool it is, but also because I want to spend just one last effort in practicing calculating a bunch of integrals, finding a bunch of antiderivatives to remind you of the sort of tricks that you've probably seen before. We're going to need to be fairly good at those skills when we use it for doing applications. So the first example we should start with, it's maybe the most basic one. We should calculate the area of a circle of radius A. So let me draw a circle. Here we go. So those are my axes. I want a circle of radius A. That's not such a bad, oh, that's a very good circle now. So we're out here at A. So the graph of this circle is x squared plus y squared equals a squared. That's basically Pythagoras. And if I make y the subject, so I bring the x squared over to the right-hand side, that's y squared. So y is going to be plus or minus the square root of a squared minus x squared. And I'm just taking the plus square root, so that's the equation of this function that's the top half of that circle. So now we're going to calculate the area. Actually, what I'm going to do is I'm going to do just 4 times the area of that first quadrant. Right, so that's a quarter circle, so my area is going to be 4 times whatever that area of that quarter circle is, and I'm going to calculate the area of that quadrant by our usual game. I'm going to cut it up into strips at x and x plus delta x, and I'm going to calculate the area of that strip. It's roughly a rectangle. So the thing I'm trying to do is I'm trying to sum up, as x goes from 0 to x is a, the height of that strip, which is y, root a squared minus x squared, times the width of that strip. So that's the area of the quadrant. I put it in quotation marks because that's that sort of rather informal way, the way you think about these sort of calculations. We're trying to let delta x go to 0, but that's roughly the sum we're trying to calculate. There's a 4 here, now I'm writing, because that's 4 times the area of the first quadrant, and the area of the first quadrant is that sum in the limit. When that sum stretches out and becomes a definite integral from 0 to a, root a squared minus x squared dx. Okay, so that's the integral we need to calculate to find the area of the circle. It's not such an easy integral to calculate. We need to do a substitution, and the substitution to make here is to let x equal, let's do a sine theta. So I guess if you wanted to think about what we're actually doing, if you want to think about it geometrically, that's the x, right? So I guess if I drew that little right angle triangle here, that's I'm making this angle here theta. Sorry, that got a little bit small. So I'm instead of using x to parameterize my strips, I'm using that angle theta. It's the same as that angle down there if you prefer that angle. Anyway, that's not important. I don't really think too geometrically. The reason I do this is because if that's my x, a squared minus x squared becomes a squared minus a squared sine squared theta, and then you can pull out the a squared, and you get a 1 minus sine squared, which is cos squared. And it's all inside this square root, and you can square root that thing. So the point of that trig substitution is to kind of use Pythagoras to get rid of the square root. So that's the substitution we're making, and to do these substitutions we're basically using the substitution formula. If x is a sine theta, then dx by d theta is a cos theta. So the little mnemonic when you're doing this substitution is you just keep in mind that we're going to replace the dx in that formula by a cos theta d theta. And so when we make that substitution, this number a that we're trying to calculate becomes, so the root a squared minus x squared becomes root a squared cos squared theta, which is a cos theta, and then the dx needs to be replaced by a cos theta d theta. I'm not quite done with the substitution because this is a definite integral. Those limits, they were x limits. I need to replace them by the thetas that correspond to those places. So we've got to think when x is 0, what's theta? Well, when x is 0, that's when we're here. So that's when that angle theta would be 0. Sine of 0 is 0. And when x is a, that's when we're here. That's when the angle theta would be pi by 2. Did I do that right? I want x to be a. Yeah, I want sine theta to be 1, so that a sine theta is a, which is that top limit. Okay? So my limits, instead of being x limits from 0 to a, they're theta limits from 0 to pi by 2. So now I've done the substitution, all the x's, including the limits, changed to thetas. And what have I got? I've got 4a squared, integral from 0 to pi by 2, cos squared theta d theta. Well, at least I got rid of the square root, but it's still a little bit of a tricky integral to calculate. One needs one more trick, which I'll just remind you of over here. You need the double angle formulae. So as we're kind of slowly moving along through all these examples, I'm slowly trying to remind you of all your tricks from calculus or from trigonometry that you've once seen, because these are all important to know. So the double angle formula is how to calculate things like sine 2 theta in terms of sine theta and cos theta. Sine 2 theta is 2 sine theta cos theta. Or cos 2 theta, that's the one we need now. Cos 2 theta is cos squared theta minus sine squared theta. So the way you remember this is like Pythagoras. Pythagoras is cos squared plus sine squared. If you change that sign, get cos squared minus sine squared. That's the double angle formula for cos 2 theta. But you can rewrite the cosine one in different ways. You can replace the cos squared by 1 minus sine squared, or you can replace the sine squared by 1 minus cos squared. So there's 3 different forms for the double angle formula for cosine. And actually we need the last form, which if I rearrange tells me that cos squared theta is cos 2 theta plus 1 over 2. And that's what we need to use here, because I've got a cos squared theta there, which is cos 2 theta plus 1 over 2. And now I'm in good shape, because now I've got something where I happen to know an antiderivative, so I can use our Fundamental Theorem of Calculus corollary. You see I've got 4a squared and I've got it divided by 2, so that's 2a squared. Antiderivative of cos 2 theta is a half sine 2 theta. Antiderivative of 1 is theta, and I've got to evaluate from 0 to pi by 2. And when I plug in 0 everywhere, I get 0. When I plug in pi by 2 into the sine, I get sine of pi, which is 0. So the only place I get something non-zero is when I plug the pi by 2 into the theta. So that all evaluates to pi by 2, which is just pi a squared, which you of course know perfectly well is the formula for the area of the circle of radius a. Okay, but that's a nice example. It reminds you of a bunch of trig identities which we needed to use there. Okay, that's the first example. The second one I'm going to do today, let's do the volume of a sphere. So this is something that Archimedes worked out, this formula originally, and you read about how that was done. But using the tools of calculus, this is really rather easy. So let's draw a little picture. So we need a sphere. So I guess I need a circle, and then I'm going to make it into a sphere, so let's make it look like a sphere a little bit. Let me try and center it so that it's looking better. So I want a sphere. I can do better than that. I know I can get this to work. This is not quite working for me today. Okay, well, never mind. I'm going to try one more time because this effect's nice, but for some reason it's not joining up today. There we go. That's what I was after. So that now looks quite like a sphere. And so what I'm going to do is I'm going to do our usual game of cutting it up into strips. So I'm going to go to x and x plus delta x. And then that strip in there, I mean, it's roughly a little disk. You see that? So this is roughly a little disk. This is a thin disk of width delta x. I'm trying to calculate volume, so I can approximate that by just a little thin disk of width delta x, and the radius at the top there, well, that'll be the y coordinate, and remember it's still y equals square root x squared minus a squared, so that's the height, that radius in there, that's root, not x squared minus a squared, sorry, a squared minus x squared, just like in example 1. So the volume of this disk, it's the area of the circle that's the base of this cylinder, which is what, pi times the radius squared, so the radius is that square root, and then times the height of the cylinder, that's that delta x. So the thing we're trying to calculate, we're trying to sum up. I guess what I'm going to do is I'm going to do just the hemisphere. So I just want to do the right-hand half of the sphere. And for the right-hand half, I need to sum up, as x goes from 0 to a, the volumes of all of those disks, a squared minus x squared delta x. So you sort of just think informally, that's roughly what I want to sum. And to sum that exactly, you just turn that sum into an integral. You take the limit as delta x goes to 0. So that's the integral that will calculate this volume. And this is rather an easy integral this time. I don't need to do anything fancy. What have I got? I've got 2 pi. I've got to find an antiderivative of a squared, which is a squared x. And I've got to find an antiderivative of x squared, which is x cubed over 3. And then I've got to evaluate between 0 and a. But plugging in 0 everywhere gives me 0. So I've really just got to evaluate at a. So what have I got? I've got a cubed minus a cubed over 3. So that's 1 lot of a cubed minus a third a cubed. So that's 2/3 a cubed, which is the formula that you probably knew we were going to get. 4/3 pi a cubed. Okay, so there's that famous formula for the volume of the sphere. Okay, so that's a nice easy one. You probably, when you saw this before, you probably were taught about calculating volumes of these shapes obtained by taking some graph and rotating the graph around the x-axis. So these kind of volumes of revolution, and you can think about that. But I never really bother. I just, whenever I have to calculate some area or volume or something, I just sort of think, what little things am I adding up? And I come up with my informal sum in quotation marks, which I then turn into the integral in the limit. And then you're away, you have to calculate these antiderivatives. So this, by the way, is called the disk method for finding volume, because we cut the shape up into these thin disks. So the final example I'm going to show you today is a slightly different method of calculating volume. So I want to calculate the volume of the apple core. Well, it's not the apple core, I want the apple. So let's call it the cored apple. I'll draw a picture and you'll get the hang of what I mean. So again, I'm starting with a circle of radius A. And this time what I'm doing is I'm taking out of this circle, taking out a core. So I'm going to remove, so this is, let me see if I can get this right, this is x equals A, and my core is a little cylindrical core I'm taking out of the middle of this spherical apple at radius B. So I'm going to remove a cylindrical core for a cylinder of radius A. Let's try again. Radius B for the cylinder from the middle of a spherical apple. Radius A. And the question is to find the volume of the remaining piece of apple. Okay, so the way I'm going to do this is I'm again going to do our usual game. I'm going to think about going from x to a little bit more, x plus delta x. And this time I can't cut into disks, so what I'm going to do is I'm going to cut, so this is symmetric to the other side, I'm going to cut it into these little, this picture's not great, I apologize for not really being very artistic. Yeah, that's a very bad picture. So what I've tried to draw here is a little cylindrical shell. So let me see if I can draw that a little bit better over here. It's got some thickness. The thickness is this delta x as usual. So what have we got? We've got this radius here, that'll be x, and the height, that's this height in here, so that's twice y, so that'll be 2 root a squared minus x squared. And so it's just this little shell, right? So I'm looking at going from the cylinder at x to the cylinder at x plus delta x. So the thickness of this little bit of cylinder here, this thickness is delta x. There's just the shell of this cylinder of thickness delta x. And the volume of the shell, well, how would you calculate the volume of that shell? What you would do is you would take your you would take a pair of scissors and you would kind of cut the shell open and unwrap it. And when you do that, it would become just a rectangular plate, like this. Let's do a bit better. That's terrible. Let me have one last attempt. I wish I was quick at drawing these pictures, but I'm not very good at it. Yeah, really not good. Okay, good enough. So there's our plate. It's meant to be rectangular, and the thickness of the plate is the delta x, and the height is this 2 root a squared minus x squared, and the width, well, that's the circumference around the cylinder, which is 2 pi x, because the radius of the cylinder was x. So the thing we're trying to calculate is the sum and we need to go from from the inner cylinder, which is at x equals b, to the outer one, which is at x equals a. So we're summing from x equals a to x equals b. The volume of the shell, which is, let me see, it's this rectangular plate. So this is a cuboid, so it's what, 4 pi x root a squared minus x squared delta x. Those are the things I need to sum up. So when I do that, I just go to the limit, and it becomes the integral from a to b, 4 pi x root a squared minus x squared dx. Hopefully you see how I'm doing this, and my picture was particularly bad here. But I'm cutting it up into these very little thin cylindrical shells, and I'm adding up the volumes of all of those shells. So now we've got to calculate that integral. So actually this turns out to be quite an easy one. And the reason it's easy, you see that x there, I always call that my friend, because inside this square root I've got an a squared minus x squared, and the derivative of that inside stuff is minus 2x. Forget the minus 2. The derivative of that inside stuff is an x, and I've got an x sitting there outside. That's why it's my friend. So that friend is the shadow of the chain rule for differentiating. Whenever I see a friend, I know I can always just write down an antiderivative straight away. What I'm going to do is I'm going to try this stuff inside. It's square root, right? So it's this stuff to the power of half. So my guess for an antiderivative is going to be that stuff inside. Add 1 to the power. I should divide by the new power. But I just kind of come up with a guess that's going to be right up to multiplying by a constant. And then I check. That's my guess. What would happen if I differentiated that? I would bring the power down the front, 1 off the power. So I would have 3 over 2 stuff to the half. That would give me all of that. But then I've got to times by the derivative of the inside, which is negative 2x. So I would have 3 over 2 times minus 2x, which is what? Minus 3x. And I want 4 pi x. So I think I've got to put minus 4 pi over 3 to get that right. And let me just double check it again. So that 3 over 2 comes out down the front. So I get minus 2 pi, and then there's a minus 2x, so I get 4 pi x. Yes, that's the antiderivative. So it's a sort of slight guess and check method. Once you spot a friend, you just come up with a guess. And then I've got to evaluate between a and b. Well, when you evaluate at a in there, you get nothing. So I've just got to plug in the b for the x. And I do seem to have made one mistake here, because I got my limits the wrong way around. It's the b that's the smaller one and the a that's the bigger one. You always go from left to right. So it's from b to a, from b to a. And now it was the a, which when you plug in the top limit, you get 0. So we're just plugging in the bottom limit. There's already a minus. The bottom limit gives another minus. So that all becomes plus 4 pi over 3. And then it becomes a squared minus b squared to the 3 over 2. So I think that should be the answer with any luck. Let's just do a little reality check. If b is 0 here, so there's no core, this should just recover the volume of the sphere. And when b is 0, that just becomes a squared to the 3 over 2, which is a cubed. Oh yes, 4/3 pi a cubed, which was indeed the volume of the sphere we were expecting from before. Okay, so I've done a few examples today of using the Fundamental Theorem of Calculus. This is almost the end of the review of calculus that I wanted to do. You see, what I'm trying to do is kind of show you all the various little tricks from calculus and from trig that you've kind of seen before, so that you remember them all. And we've got all the tools at our disposal when we start getting to new interesting applications of calculus. I'm going to do one more thing along these lines at the beginning next time. I'm going to talk a little bit about arc length. So we might actually calculate the formula for the circumference of a circle, which I used just a few minutes ago. But I think this is the place to stop today.